Hello, calculus students and general seekers of truth. We are now going to look at one method of approximating the error of a series. Now, this is really review here, but I will show you how the review question here applies to the first example. So let's just think about an alternating series, not an alternating Taylor series, just a generic alternating series. For example, something like this. We'll start at n equals 1 to infinity of -1 to the n plus 1. And this is really an example of 1 over n. Okay, so if we list this out, this is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, and so on. Okay, so I will call this S. And I will call, let's say if we were to approximate this section here, S4. Okay? So if we were to, we can't actually compute this series because it's an infinite number of terms we have to add up. But let's say if we were to use the first 4 terms to estimate, what would S minus S4 be equal to? Well, the alternating series error bound that we talked about before would say that S minus S4 in absolute value is at most 1/5. In other words, the next term here in the series. Okay, so the alternating series error bound says that the partial sum of an alternating series that converges. I'm sorry, I should mention that this series has to converge for us to talk about any error at all. Okay, so if it's a convergent alternating series, then the partial sum is at worst the difference of. I'm sorry, let's say that again. The exact value minus the partial sum is no larger than the next term in the series. So the S here is the exact value minus the partial sum is at most the next term in the series. And there's a proof on this from one of the previous videos. I'm not going to get into this proof today, but I just want to remind you of this, and also in general. The exact answer of any alternating series, so this again only applies to alternating series that are convergent. Okay, so if it converges, then all of this stuff applies. From n equals 1 to infinity, a sub n minus n equals 1 to k of a sub n, so the kth term. The difference between the actual answer and the partial sum is at worst the absolute value of the next term in the series. Okay, and this provides for us a very nice. I need to erase these dots here. That's not factorial there. Okay, so this provides for us a very nice way to find and estimate error when we do our approximations, as long as you have an alternating series, as long as we know that it converges. Okay. Okay, so let's look at our example here. The function g has derivatives on all orders, and the Maclaurin series for g is this. Approximate the value of g of 1/2 using the first 3 non-zero terms, and find an upper bound for the area of this approximation. So a couple things we know about this series already, and this is from our homework problems, or we've proved this previously, that this has an interval of convergence between when x is between -1 and +1 inclusive. Okay? So we already know that this converges. Now, when x is equal to 1/2, let's see what we have here. The series becomes 1/2 over 3, so that's 1/6, minus 1/2 cubed over 5, so that's 1/40th, plus 1/2 to the 5th over 7. So that's 1 over 32 times 1 over 7. Okay. And if we were to keep on going, you can see that the series alternates. Okay. So when g is equal to 1/2, when x is equal to 1/2, we know that the series alternates, and we know that it converges because the interval of convergence is anything between -1 and +1. So if we were to approximate it using the first three non-zero terms, well, here they are: 1/6 minus 1/40th plus 1 over 32 times 7. Okay, so I've done this separately and got this result. So g of x is some mystery function that we don't know. We don't really know what it is. We just know that this series here is a way for us to approximate g of x. And if we use this series to approximate g of x at 1/2, we get this number. Now the question is, how good is this of an estimation? We don't know the exact answer because we don't know what g actually is, but we can actually predict what would be the worst case scenario. Okay. So this series here alternates and it converges. We did this in the homework. We determined that it converges as long as x is a number between -1 and +1. And because it converges and alternates, we can use this alternating series error bound. And all we have to do is calculate that. We can say that the error, or the remainder, is no worse than the next term in the series here. So the next term in the series would be x to the 7th over 9. And x in this case happens to be 1/2. Okay. So we end up with the absolute value of, well, there's a negative here, but the absolute value kind of takes care of that. So you end up with 1 over 2 to the 7th times 1 over 9. Okay. So if I actually work out all these details, then all the arithmetic here, then we get, this is 1 over 2 to the 7 times 1/9, which is 1 over 1152, which is this number. So what that means is that this calculation is no worse off than this result. Okay? So that means the exact answer, g of 1/2, is somewhere between 491 over 3360 plus 1 over 1152 and 491 over 3360 minus 1 over 1152. Okay, that's what this is really saying. This is our error. It's 1 over 1152, and that means this calculation that we did with 3 terms is it's not exact, but it narrows down the exact answer to whatever these results are. Okay, and you can calculate this on a calculator yourself just to see what this number is, but it's actually some pretty small. It's a very, very small interval. Okay, so this is an example of us putting the alternating series error bound to work for us, and this is what we get. Now I'm going to end this video here and move on to some other cases where we're not able to use an alternating series error bound. Thank you for watching and have a wonderful day.